Okay, good morning, good afternoon, good evening, everyone. So, in the last class, we discussed about different types of scans using the Nmap. We did Xmas scan, we did a fin scan, SYN scans. We did a lot of scans to understand how exactly the scan works. And if it is an Nmap scan, how do I find it? If it is a legitimate scan, or how do I differentiate that? That's something we had a closer look on those different types of Nmap scans in the last class. And today we will discuss about the TCP delays. And we have few more things to discuss. We have to talk about the TCP delays. How do I find the TCP delays? And then we will talk about DNS. We'll do a DNS and how do I find the delays in the DNS and how exactly I should use a Wireshark to capture the DNS packets. And what are all the other informations I have inside the DNS? That's something I should focus on when I'm troubleshooting and also to understand the process of DNS. Because we know that the how to say that DNS plays a very vital role in your network, right? So when you connect to something, we can't remember the IPs. So DNS plays a vital role, and how we are going to troubleshoot the DNS related issues, and we will understand deeply about how DNS exactly works and what are all the different pieces of DNS that works together to establish a successful connection to the destination. Then, if we have a time, then we will do a MTU comparison with MSS, maximum segment size. We will do a GRE lab for it. And then followed by that, if time allows us, we will continue with the remaining topics as per the course content. So first, let me talk about the TCP delays. Let me open up the PowerPoint. Let's take the simple diagram here. Wait 1 second here, my connection. Yeah. So you got your web browser, and you're doing maybe primarily you will do this, right? Google.com. Let me take a different color. So when you type in any website, like you can type in google.com, yahoo.com, whatever it is. So how exactly the whole process happens, and what should I see in the Wireshark? Your DNS request goes out of this computer, and I should get a DNS response back from the destination. So this is a big difference between the TCP and DNS. So like TCP, we don't have a three-way handshake in UDP. We know that. So far, the most commonly used transport protocols, um, so far it is two, and there is few more. It is still there, but the most widely used, the applications are most widely using these two transport protocols. So UDP is a connectionless. We say it's a connectionless protocol because there is no sense and act mechanism here. There is no guarantee that your packet is properly delivered to the destination. It may reach, it may not reach. There is no concept like there is a mechanism of retransmission, but there is no mechanism to get your acknowledgments for your packets. You never get an acknowledgement for a packet in UDP, unlike TCP. So the DNS is using the UDP protocol. So there are only two packets. I will send a DNS request and I should get a DNS response back. But on top of that, we should understand a bit about how this whole process happens in the backend. So that helps you to troubleshoot better, to understand the whole process of DNS. So this is my client PC. So this is your ISP, or it can be your modem. You got many devices in the middle, and you got your root server, top level domains, TLD, your authoritative server, also called as a name server. So these are all the different pieces that's whole. I mean, these different pieces are interconnected, and the whole process of DNS happens with all these different pieces talking to each other. That's how your whole DNS flow happens. So here, I can't remember each and every destination IP address. That's purely routed, and what there is, I mean, the job of the router is to route the packets. Any device, it can be any device, the layer 3 devices, the job is to route the packets, and it's going to route the packets to the expected destination, and it will help me to find the destination. That's how the whole routing works. But here in the DNS, what's something we should understand? So the first key component of the DNS is that you should know what is a DNS resolver and different types of queries. It's an iterative query and recursive query. That's it. I mean, if you understand this, you will understand the whole process of DNS. So when you type www.google.com, It's your first step. So what happens the second packet? So we don't know the IP destination IP address, right? That's a question mark. So we should know the IP to route the packet. But right now, you just imagine this is a computer. This is the first time it is trying to establish a connection to google.com. So I don't know where is this destination IP address. So what happens here? The PC will do a DNS request. So from this PC, the DNS request goes out. So there in your computer, we will define something like name servers. You would have seen that that is called as a preferred name servers. That's not static. You can give your name server, that is a custom name servers you can give, but generally in the enterprise design, they have their open DNS, right? They don't rely on any public DNS servers like Google or any public. There are multiple public DNS servers, but the most popular is Google. So for this example, so most of them we use google.com as a DNS server. So it is a preferred DNS. You can give any name server you want. So your all your DNS request goes to this particular server. Whatever you define in your network, that goes out. So I'll show you where to see that. You guys know that. That's how your DNS query goes. So that for this DNS request, right? Whatever I define here, example, if I define my DNS server as a Google 8.8.8, so the request has to go to the DNS server directly. But example, let's say this is an enterprise. So I got my DNS something like 172.21.21.1. So now who becomes a DNS resolver? This guy. It becomes the DNS resolver now. So it will try to do a DNS resolution. I mean, the PC sends a DNS request. And in this case, example, I'm telling my ISP owns this DNS server 172.21.21.1. So it will look for its cache. And I don't know where is google.com. So the recursive queries, it keeps happening. It keeps happening until it finds the destination IP address. That's the whole objective of the DNS process. So at this point, I don't have that the the IP address of the google.com in my local cache on the server. So again, what it does, it will do a DNS request again to the root server. So whenever you type something, you will have dot at the end. So it means that it is called as a root. So inside the cache, I don't find it. So it's going to, it goes out because my first hop is this server because I defined this as my DNS server and I don't have the cache information for the google.com. So the request apparently hits the root server and I get a referral request back from the root server. So what's this root server is going to tell us for this request? It comes out of this DNS server now, 172.21.21.1. When it comes out, so the root server is going to tell us that I don't know where is your IP address of this, but I know where are the .com servers, and I know where are .in servers. So in this case, you want to find something on .com. So it's going to tell us that the root server is going to give us that these are all the list of servers you have to reach out, your top level domains. The domains are .com, .in. These are the list of top level domains. So from this referral request back from the root server to this the resolver. So the resolver now it's going to see the referral code. Okay, so this is my top level domain now. So now my request has to go to the TLD, top level domain for .com. So I'm going to reach out the server who is responsible to hold all the information about .com. So once it hits here, the TLD is going to give a referral code about your name server. Name server of what? Name server of google.com. This is a referral response again, coming back to the resolver. So the resolver is doing everything on behalf of the client because he is the resolver. So this every request that goes out of the resolver every single request is a recursive query. So once it hits here, now I know where is this name server. So who is the authority name server for google.com? Example, it's an 8.8.8 is the IP address, but the name server can be something like example 80.80.80.80. So again, the request goes out of this resolver. It comes back again. The request comes back again to google.com. So now I know where is the name server 80.80.80 and it hits here. The name server is going to tell us, okay, this is the IP address. Sorry, this is the name of the IP address that's bounded to. That's google.com. You get a response back here. Now your actual packet is routed back to 8.8.8. This is a whole process of finding your destination URL. So this is called as a recursive query. So in the Wireshark, what should I see in the Wireshark? As I said, this is a client now. This is a server. So now we know that DNS request goes out. The whole process happens, what we discussed, and we should get a DNS response back. So the ultimate goal is to find the URL, FQDN, fully qualified domain name for the specific URL. Who owns this google.com? I should get a response back to resolve it. So if DNS server is down, your client is going to do a retransmission. But if you have a valid DNS server for your DNS request from the client, you will get the DNS response back. So in the Wireshark, you should see something like a name servers. They are the authoritative name server for the specific domain and the FQDN. I'll show you how we can see those authority name server fields in the Wireshark. So on top of this, like your IP packet, we see something like a TTL, time to live. That is used to find the number of hops it has to take. And we discussed this a lot. If you really see the significant TTL values there is actually your routing is happening. There is no problem with routing. We discussed this with multiple use case scenarios. So now in the DNS, TTL stands for time to live. Example, I would say it is 15 minutes. What if a Google DNS is changed with a different IP address? Example, if a google.com, and if they are changing the IP to something like 9.9.9.9, and an example I'm telling. So the DNS response is not valid after 15 minutes. So if something changes for the new DNS request, it's going to overwrite my value with 8.8.8 is replaced with 9.9.9 after 15 minutes. When it is doing this, after the, what is that? After the time expires, it will do the other DNS request. For that, I may get a different response back. So the TTL is the time given to have the DNS cache. And if it is flushed or if it is something changed, then again it has to do a DNS request and it should update its database with the new DNS response messages. And sometimes what happens in the Wireshark, what should we focus on? This is again a client. And this is as a server. Your DNS request goes out. You get your DNS response. The DNS request has sent when I see TCP, sorry, I see the delta time has 533 milliseconds. The request has sent when I see the network latency is 533 milliseconds. It goes out. But the DNS response, I got the DNS response back after 2 seconds. Example. So this is called as a DNS delays. So after the request, how long the client is waiting to get a response back? So why this particular DNS server is experiencing slowness? Is it about the network or the DNS server is too busy in answering the queries, multiple queries? That's something, how do we find it? I'll show you in the Wireshark how do we find that. But this is the logic of it. So how long when the request goes out and how long I'm waiting to get a response back from the server? Is it really the server is slow or busy doing the other queries? And because of that, I get a slow response back. Because of that, my web page might be loading slow. And I can't blame my network because of this. So how do exactly I spot the problem with DNS instead of just thinking about it can be a network issue? That's something today we will see that in the lab. And one final piece of information about the TCP delays. So this is again a client and this is a server, and we know that this is a peer-to-peer connection. So when we look into the packets, right? So we are always focusing on the network round trip time. We call this as an RTT, network round trip time. But in the TCP, the same thing, we have a filter in the Wireshark with the delta time. We have the similar option with the TCP delta time. I'll show you how do we find it. So the TCP maintains a timestamp with a delta time where you can figure out, okay, my network round trip time is fine. Okay, so it shows that for my SYN and for my SYN ACK, I see something. I send a SYN in maybe example. This is all an example. So 330 millisecond. And I got a SYN ACK back after waiting maybe I would say 380 milliseconds. So the total round trip time is the client is waiting for 380 milliseconds to get a SYNAC back from the server. So my network is good. But what if the TCP connection, right? So I send us, there is some conversation happening until this point, since SYNAC ACK, your round trip time is fine. But at one point, it spikes somewhere around 3 seconds. I'm talking about only the TCP conversation now. There is no problem with the network. But in my TCP conversation, I see the delta time spikes to 3 seconds. So the client has to wait 3 seconds to get a response back from the server. I'll show you how I can find that in a particular stream. As I said, the TCP request goes out. We got two requests. One is going to google.com. And the other request, it goes to yahoo.com. So example, this is stream 0. And this is stream 1. So every TCP connection that goes out of your computer, it has a different stream. Every TCP connection has its own stream stamped into it. That's something we'll see that in the Wireshark. How do I differentiate that? Because there are lot of TCP connection that should be, keep happening frequently in your computer. But how do I focus on a single stream, and how can I troubleshoot that problem? And how do I find the TCP delay? And how I can exactly say that it is a problem with the TCP and not with the network. So we will see that practically how to do that. So it's all about the glimpse of what you see and how you should understand the Wireshark layout and how Wireshark interprets those details for you. So I have this PCAP. I'll send it across to everyone. So this is to find the TCP delays. So how do I find that TCP delays very quickly in one single option? If I click on this, I will open up this option to show you what is the exact filter I'm using here. It is tcp.time_delta value. Again, how to do that? So if I click on this option, you have your filter. You have to type in tcp.time_delta. You can give your label, you can give any name. Here I gave the TCP delay to say that this is a TCP delay. And if I edit, and if you give a filter tcp.time.delta, you can give the highlight, it is highlighted blue color. Yeah. So this is TCP delay. If I click OK, it's going to tell us that tcp.time_delta. So this is a filter. I said how to do that. But how do I find that in the layer 4 header? How do I find that in the TCP header? Go to any header value. Click on the TCP header, scroll down. So you will see something like a timestamp. So I am focusing on this option, time since previous frame in this TCP stream. What I'm going to do here, right click on that time since previous frame in the TCP, apply as a column. So it says that already it exists. When I click that, I should see an option like this. Again, go to the layer 4 header, TCP header, scroll down, come all the way back to this option, time since previous frame in the TCP stream, right click, apply as a column, and you should see your column right over here. TCP delay. So now in this capture, we have a slowness. So how do we find that? And as I said, there is one more option here. Again, come to the TCP header, come to stream index, right click, apply as a column, and you will see a stream index option here. And if you look at here, see, this is the first TCP stream going. This is my client and this is my server. So in the round trip time, it is good. I don't see any latency. This particular conversation so far, yeah. And you can see the two arrows here. This is the request goes out of the client 24.6.173.20. If you see this arrow, it indicates that the packet goes out from this IP address. It goes out. It does a GET request. And if you see the packet number 6, you get an HTTP OK message for it. So do you see any latency here? It takes just 849. You can see the same value here. You can compare. And always ensure that your packet numbering are proper. Here, if I see the number 1, 2, 3, 4, 5, 6, it should be properly sorted here. Otherwise, you can't get the proper values. So my GET request goes out and I got a response back, OK message, and it took 800 milliseconds. So I don't see any latency in this particular stream. So if I give tcp.stream equal 3 in this particular packet, what happens here? I didn't change anything. I see SYN, I see SYNAC, I see an ACK. And if you compare these three values, but if you see the stream index is different. This is stream index 3. We saw that for stream index 0. So this is a different TCP stream. And you see this different GET request. It requests for a different message from this HTTP server. And you get a OK message. But if you actually see this, this is 2 seconds. Delta time, it says it's 2 seconds. You have to compare your TCP delta time now. If I erase this, you'll see this better. And if you see this now, it took 2 seconds for me to get a response back for my GET request. So again, I'm repeating this. You can see this in SYNAC ACK. This is a different TCP stream to the same destination, but it requests for a different HTTP request. Yeah, it's for a different message. It is expecting a different data. So the GET request goes out. You can see these two arrows. This option that's facing outwards, it's going out. The arrow which is inwards is the packet coming back from the server. And I see this, it took 2 seconds, 2 seconds, 675, 2.5 seconds. Yeah, exactly. It takes 2.5 milliseconds or 2.6 milliseconds here to get a response back from the server. Because this is a client, this is a server, you see that. So the client is waiting for 2.67 seconds to get a HTTP OK message from that. It's downloading something, it is doing something, but if you want to spot a problem, so the GET request went out, so the client side's proper. So far, if you see until this point, right? So until this GET request, it took about 634 milliseconds here. The request goes out at 173 millisecond, but I had to wait for 2.67 milliseconds to get a HTTP OK message for my GET request. And as I said, if you click on OK, you can see these two arrows. So you can figure out the request goes out in 634 millisecond and I got a response back after 2.67 milliseconds. So it's a problem with the server. The server is not responding for my GET request. So I had to wait for 2 seconds here. So this is how in the capture you should see. And if you see this, this is a retransmission happening here. This is a server and this is a client. If you right click, apply conversation filter, TCP, you will get the same information here. So how do we find the TCP delays? So as I said, again, I'll repeat this. So the TCP delays, you have to click on the TCP header, go to two options, click on your stream index where you are facing a problem with a particular get request and get response for if you're doing something, you're trying to test something, you have to apply two filters. One is the stream index filter, the other filter is the timestamp. It's in the all the way back in the bottom of the TCP header. You can right click, apply as a column, you get this TCP delta value. It can be a bigger, it can give a different name. You can click on it, right click, edit column. You can give your own name. I have given this as a TCP delta. And I have shown you that how to do this filters. So TCP delta, TCP dot time underscore delta is the filter. You can use it to quickly spot your TCP delays. You can see this TCP dot time dot delta at the bottom here. Sorry for that. So this is how you can find your TCP delta problems. Sorry, your TCP delays. And now let's do a simple capture, and we'll try to figure out what is the normal capture looks like, and do we find something there. So now let me open the Wireshark. Oh, okay, I'm doing the capture on my Wi-Fi connection now. So I'm trying to do yahoo.com. So now again, so how exactly I will start my, okay, 1 minute, I think we have to wait for a few seconds. It's loading. Okay. So if I do DNS matches double colon Yahoo double colon enter. So this is a quick filter when you want to find a DNS. So I gave this DNS matches underscore whatever the value you want to give. I'm looking out for a Yahoo. This is a string, the value, whatever you want to search for, you can give your values here. Click on this plus option here. The right hand side, right over here, you have this option plus, hit on it and give a label name DNS. Just you can give a DNS. It's a maybe you can give a DNS query. If I click OK, I see an option here. So if I click this, you can see the matches value, and you can give a value, whatever value you want, you can find. So we are not going to the DNS part now. We are going to the TCP delay. Yeah. So I'm just scrolling here to see, do I see any packets for the HTTP? And I'm going to give and TCP dot port equal 443. Or maybe I want to see a packet for TCP. Okay, let's just do a TCP. So I'm just randomly choosing a packet. So this is a TCP connection between my computer and my modem. I'm going to right click this. We know that we both are in the same subnet. We discussed this in the last class. So I'm just trying to find the TCP connection between my modem and my PC. And I'm going to apply a filter as TCP. So it is telling that my stream index is 291. Do you see any response, delay response here? This is a proper TCP connection. And one more thing, you have to ignore your resets, your fin packet, your reset packet. You have to ignore all that. You have to purely look into your actual data communication, your actual payload. You should not focus on your fin packets or anything else for your delay. That should be excluded for your analysis. So I see SYN ACK, I see push packet, even I don't see the SYN packet. Out of this, I don't see any latency right over here, either from the client to the server. And let's see if we can find anything with HTTP. Stop this capture. So let's go to um, this is something with Microsoft conversation filter TCP. So I see 200 okay, and if you compare all this, I don't see this delta time increase more than, even I don't see anything more than 1 second. So if I click on this TCP delay greater than 1 second, see for a different indexes, I see a different spike here. When you see 6 milliseconds, I see 5 milliseconds here. As I said, this is the complete TCP dump. So if I want to see the conversation only between these two, the delta time is too high. And as I said, you have to sort the value here. 26, 34. So I go to any conversation here, example, the delta time is too high here. Okay, if I go here, conversation filter, and if I give a TCP, so connection established. I see a lot of TCP keep alive here. So if you ignore all the other packets here, you leave about the keep alive and all this, because if nothing happening, it waits for 27 seconds. So you don't want to focus on that. As I said, you have to look for your actual payload. Is there any kind of get message? So it's a connect request goes out and the connection established, and I don't see any TCP delta values. That's why I am telling. Don't mislead it with the values you see. Whenever there is a spike, don't just think that's a problem here. We are just purely focusing on the actual payload. So for my HTTP get request and get response back, what is the time taken? That is something you have to focus. And you can compare your values. You see the same 400 milliseconds here. You can see the same 400 milliseconds right over here. This keep alive is excluded. Your keep alive, your fin packets, then your reset packets are excluded from this analysis. If you're troubleshooting, you should focus only on the get request and get response back. And if it is trying to establish a connection, it established a connection in just 400 milliseconds. So that's how you should analyze this. You should practice few packets, then you will understand better about this TCP delays. So now we are going to the DNS. What is a simple DNS request looks like? So let me take this capture. anything with the DNS packet. DNS capture DNS. Okay, let's take this option for DNS. Let's wait for a few more seconds. I think it's a big capture. Okay, so I got this packets back. Okay, so I got a response back here, right? For my google.com. Yeah. So you can follow the same arrows here. So as I said, the DNS request and response. We are looking for 2 packets and it is running on top of UDP. And sometimes it uses a TCP. But now we are primarily focusing on the UDP. So let's take this request. You see this is using UDP. So if I do a conversation filter and if I do an UDP, so only 2 packets we are focusing on now. The source 192.168.0.135, it's trying to find, okay, let's take a different capture. Let's do a different capture. I think I got a capture here. Where do it? I go to this Windows PC and maximize this option. Let me open the Wireshark. I'm capturing the packet on my Ethernet interface. Let me close this. Let me do dns.google.com. We do a DNS. Stop the capture. Conversation filter. Go to UDP. Okay. So my network round trip time. So I sent a request in 0 seconds and I got a response in 285 milliseconds here. And it is using an UDP. So what is the response I got it here? The answer, what I got it for. It's remote setting production web services.net, but we are looking an option only for. Okay, what did we try? 1 second, let me see what we tried here. We tried to open the public DNS, dns.google.com. So if I do DNS matches Google, I'm trying to find the name resolution for google.com. So if I do a right click conversation filter in UDP, Now I am doing this to this guy and I got a response back UTP port 53 and it's going out. This is a server 53 and I got a response back to the client. And this is my authority name server. It is telling me I want to see one more option, what I'm expecting here. DNS matches Google. Yeah. So dns.google.com. So when we are doing a request, yeah, this is something I want to see. So this is a response I got, right? So conversation filter UDP takes me to different. Okay, now we are fine. Okay. So this is my source 122.160.50.65 and it goes to the destination 8.8.8, right? Because I think I have configured the DNS as 8.8.8. I'll show you that the command prompt. So for this, if you see this arrow, it goes out from this computer and I got a response back. And the answer, what I should see here, it is telling that what are your DNS answers? You got two DNS servers. One is 8.8.8 and 8.8.8.4. So we tried to do a name resolution for 8.8.8, dns.google.com. If you see this, this is dns.google.com and this is an IP address of it. So it gave an IP address in response back. So this is the IP address. So this is the A record value, address record. So if you compare this value here, it took 211 milliseconds for me to get a response back from the server. This option I'm talking about, the time to leave, it's 10 minutes and 10 minutes and 19 seconds. This particular record is active for 10 minutes and 19 seconds. And I'm going to apply this as a column here. And you can right click on it, edit the column, and you can give DNS time, TTL. You can give DNS TTL. If I click OK, why haven't saved this? Click on it. What is the option I see? Oh, sorry, I didn't apply the filter. Yep. So the DNS space TTL is the name I have given for this particular column. So this is DNS TTL. I'll come back to this. So for now, so this is how your DNS request and DNS response comes back. Yep, I have something I have to change this DNS filter exactly. So we'll see that in the next class. So now we are in the basic of DNS, so I don't want to confuse you with those options. But the TTL, as I said, it's valid for 10 minutes and 19 seconds. If it is more than 10 minutes and 19 seconds, then it's going to do again, it does a DNS request again to see if there is any changes. If there is no change, it's going to update the same database, or else it keeps changing. This is purely about the DNS response. So, and one more option I want to see is the name servers here. So the query is for dns.google.com. So this is for the query. I got this answers. And also I am interested in looking at the servers, name servers. So it's going to tell us this, who is my authority name servers. I'm looking for that option to figure out. Where is my authority name server for this particular request? I see the answers, but I don't see the name servers of it. Name record they're doing for Google one. Okay. I think I have to do a different query to figure out that query. I see that. I don't see those name servers. Let's try with a different query. Let's try to do with a different query, and let's try to do a capture again. If I try to do yahoo.com, before that I have to fire up my Wireshark. DNS matches yahoo.com. So this all the different IPs that's been mapped to yahoo.com. I should see an option here for name servers. That's something I'm keen to see. So do I see the answers, but I don't see the servers. Okay, no problem. So I'll research on this and I'll get back to you. But we should see that option. We should not only see the for the DNS query, what is the response back? Yep. Because for this particular Google Yahoo.com, this all these IPs are mapped to it. It is load balanced across, right? And then now we have to figure out who are the authority name server for this. Who gave this responses back to us is something we are hunting for. So now, how do I find the DNS delays? For that, let me open this. I'll show my capture parallelly. So if you click on this filter, edit, and I made this filter as DNS.time greater than 1. And if I copy this, I don't think it works there. We have to type. Doesn't work. So DNS.time. DNS.time greater than 1 second. So if I go right click, conversation filter, UDP. So this is a query and this is a query response back. And if you see this time value at the bottom, so I got the response after 1 second. So the request went out and I got a response after 1.024 seconds. So this is not actually very good because we are using a simulator. It should always, again, I'm telling you, it always happens in less than a second. So if I do DNS.time greater than 2 seconds, if you look at this, it took 3 seconds for my DNS resolution. If I see a DNS resolution happens within 600 millisecond, .6. Okay, this filter is not working properly. So DNS greater than 1, it's showing as 3 seconds, 1 second, 2 seconds. So everything greater than 1 second is a slow connection. So I should see there. So whatever happening within the millisecond, that's a good connection. There is no problem. So if something jumps beyond 1 second, then something why this DNS server is responding slow. That's something you have to look into the DNS server. And what else we have to check? We have to check for the UDP port. The same option like the TCP, how we use UDP.port equal 53, because the server listens on this particular port. If you scroll up, you can see this is port 53. This is server is responding back to the client. 8.8.1. Let me circle this. So this is 8.8.8 and it is using port 53 here. And this is a client, right? This is server and this is a client. This is a server and this guy is a client. So whenever you want to see the responses, so your actual DNS resolution is happening, how do you check it? So you have to type in the filter udp.port equal 53. Then you can see all your responses, DNS responses coming back for your requests. And if you are interested in a particular conversation, right click, conversation filter. And if you give an UDP, you should see that. So this is all the queries. It went out. Let me scroll this back. So if you see this is a request. It goes out from this PC and I got a response back here. And if you see something like a replay code error, you should see the error code here. But so far now you got a response back and you don't see any error right over here. And if you see, this TTL is just 1 minute for this particular record. So now the other options, what you should do in your Wireshark capture. So you have to go to edit, click on preferences, go to the name resolution. I think this is old Wireshark. You should have an option to add your custom DNS. I don't see that option here. Max Mind, I see that. Let me go to my capture, sorry, my Wireshark. I'll show you that. Go to edit, preferences, name resolution. You have an option like a DNS server here. To edit, I didn't give anything. You can give, let me check my config. IP config all. For me, the DNS server, it is telling that it's 192.168.1.1. If I do that, I have to click on this 192.168.1.1, right? Yeah. So you don't want to define any ports here. You just define your DNS, click OK, apply OK. I go to Wi-Fi, cancel this, stop it, go to edit, preferences, name resolution, resolve network IPs. If I say again, I'm showing this option. So edit, preferences, go to name resolution, edit, add your DNS server, what you should see there. You would usually you get this after your DHCP packet. So your in the DHCP packet, we'll discuss this in the future class, but on top of this DHCP packets, it's also give you the DNS server details. So you have to update that DNS server detail here. So here I see this is my DNS server detail. I see this is my DNS server, my modem. So I gave this here. Click OK, and also you have to click on resolve network IP addresses. Apply and OK. Click on OK here. It should actually resolve your DNS here. It resolve name, but it's not giving any name here. Why it is not resolving? Let's see. Edit preferences, go to name resolution. This is my DNS server. Let me try to give my port number 53. Click on OK. Apply OK. Even that, I don't see any resolution, but the packet stopped. Let's do a capture again. Continue without saving. Stop the capture, edit preferences. Let me go to name resolution, edit. Let me give 8.8.8. Apply. Okay. Again, trying to find why it is not happening. Freezed, waiting for it. Name resolution. I'm telling, okay, resolve IP address. I didn't give it. Apply. Freezed. Waiting. Yeah, it works now. So if you look at this, this is all the requests coming in from Zoom communication. My PC is right now, we are in Zoom session. I see this destinations. And if you want to customize your source and destination, when you're troubleshooting something, you can give edit, resolve name, and you can give your own name. Example, for this address, if 192.168.1.4, I can say something like a client. Lots of packets going on, I think. It's freezing. Yeah, now you can see this request is all telling that this is my client and this is going to this destinations. So this is I'm connected to Act Internet. So you see this connection back for the Act Internet. So this is very helpful feature where you can figure out what exactly it's talking to. So right over here, I can see, okay, this some communication is happening to the Act Internet. And there is one more option I want to tell you that's very useful. You have to go to statistics. There is that statistics, resolved addresses. Yeah. So you can see here, it's a bird's eye view where you can see. So this is, it says it's an ACK internet. This is INA connection. What else? This is telling that this solves something. Okay, we don't want to look into it. So if you see this, it distinguishes this is an ACK internet connection. This is a multicast address. So how do we see that? You have to go to statistics, go to resolved address, and you can see these values. And you can give something like a host. You can see all this public IP address and their domain name. The left hand side, you see the public IP address of it, and the right hand side, you will see the name resolution happened for it. And you see the ports being used. So port number 53 is used and it's using UDP. When you're troubleshooting this particular option, when you customize this value, when you see a connection between the client and server, it helps a lot. And one final option, edit again, go to preferences, go to name resolution. You have to give this option, resolve transport names. So what it does, it is going to tell you all this well-known ports. See, 443, if I remove this, you will know the difference. Edit preferences, and if I go to name resolution, if I give resolve transport names, uncheck. Waiting, it's not responding. So now you don't see those options here, right? So I don't see this well-known port numbers. It is not telling what particular protocol is using this particular well-known port. If I go to edit preferences, go to name resolution, resolve transport names, it's going to tell me the well-known port numbers there. So again, now I got this option here to see the well-known ports. If it is using a DNS, do I see those port details there? Doesn't show up. If I give HTTPS TCP.port. Yeah, for this, I see this option here, right? So I know that, okay, this is an HTTPS connection that's happening here. So it's going to show you the some well-known ports. You can explore more for other options. So this helps for your troubleshooting. You can leverage this options to troubleshoot better. And one final capture, we'll see that's something, this is a capture I've taken when I tried to access gmail.com. It's loading, waiting for it. If I give DNS, yeah. I don't know why I don't see that with our capture. Generally, I want to show you this whenever you're doing a DNS request, right? So here I'll tell you. So the query goes out. So it's trying to find accounts.youtube.com, right? But we don't know the IP address of it. We are looking for the resolution. And if you look at this arrow, we got a response back. And it is telling that this is the IP address that's been mapped for your request. So the request is for YouTube accounts.youtube.com. You can see that. So the answers for accounts.youtube.com. So these are all the IPs that's been mapped to it. So on top of that, if you come down, drill down here in the answers, you see an option authoritative name servers. So this particular DNS name server, it's holding all these records. See, all these records are manually or maybe scripted. So all these records are inside this name server. Again, I'll differentiate this. So all these records are inside this name server. So who is the name server? What is the IP address of the name server? You look at this, both are different IPs. This is all comes with 173.194.35.34. That is the answers you get for accounts.youtube.com. Canonical record is something we will come talked about that later, but here in the very beginning of this class. So this is the name server. So what is the IP address of this name server here? This guy, yeah. Let me take a different color. So all these are the name servers. So example, in this case, this is the name server IP address of the name server is 216.239.38.10. This guy holds the record and he's telling that example, this is the IP address of the accounts.google.com. Yeah. 173.194.35.50. So this is the answer we are looking for. But who gave this answer? Who holds this record? this guy name server holds the record for this, the A record, or can be a C name record. This is all inside, but who is holding this? Who is the authoritative server, name server for this records? This guy for Google. So in your company, it's similar to that. You have your resolver, that is your DNS server. So externally, somebody is trying to access, example, if this is a Sianets.com. Let me take this different. This is not, I couldn't write it properly. Let me change this. Yep. So for Sianet, you have your DNS server, that is your resolver. You got your authority name server. So this your actual DNS server holds the record. So it does a recursive query. So somebody is trying to access Sianets.com. So this is your actual name server. It has a public IP address that's routed, but your DNS is behind this name server. So it does a recursive query. Somebody is asking the name record for a record for the Sianets.com. Can you give it? So that's how this response goes out to the actual client. So you should see all these options when you're troubleshooting it. It helps better. Do I see the proper name server? Do I see the proper record for it? You can look for all these options when you're doing your DNS troubleshooting. So what else? We did a UDP analysis. In the next class, we'll do a TCP. I think, yeah, we are good with this. So I'm just thinking, is it something I have to cover? Anything else? We covered TCP delays. We have to look for HTTP delays, and we will be doing DDoS attacks testing in the next class. And top of that, so we got one more thing. What is that? The GRE tunnel is something we will see how this MSS adjustment happens. That is an additional, that's a bonus topic. Yeah, that's something we can continue in the next class. Now let me stop this.